Hello, my name is Peter Corless, and today I will be telling you a true story about a data center disaster, the kind you never want to experience yourself. Yet in this industry, you have to live every day imagining, what if it did? It's precisely the kind of disaster site reliability engineers are paid to think about and plan for. It's exactly what an application architect needs to design their systems to route around, to keep operating nonstop regardless, just in case it ever happens. Because if those folks didn't do their jobs right, it will be a nightmare scenario for DevOps if everyone has been too busy to think about things through adequately upfront. So what can be learned about application resiliency when your data center burns down? A tremendous amount, in fact. So my name is Peter Corless. I'm the technical marketing manager at ScyllaDB. I listen to our users' stories and discover wisdom in each to share with our other practitioners in the industry at large, whether through blogs or in technical presentations like today. In my career, I've also done a fair share of strategic simulation and role-playing game design. So it's a natural inclination for me to posit what-ifs. I think it's a vital exercise for all organizations to run through scenarios to make sure that if disaster ever actually befalls them, their plans and playbooks will actually meet the real-world challenges of the day. So imagine you're fast asleep when your mobile keeps ringing. It's the middle of the night on Wednesday, March 10th, 2021. Groggily, you take the call. At first, people aren't exactly sure what's happened. Some nodes went offline. You log in. Yikes, look at those dashboards. Soon, the worst rumors are confirmed. The entire Strasbourg data center where your production database is running is now completely engulfed in flames. Okay, now you're completely awake. Even if you've done all your due diligence, planning, provisioning, the most experienced individual is still going to start pacing the room and doing a mental checklist of all their contingencies in the face of such news. Stop and think about your own deployments for a minute. What would be your first order and second order checklist items to start going through? Plus, while you are trying to solve for your own organization's issues, keep in mind that this isn't just a personal problem only affecting your domain. The data center provider is facing the fact that hundreds of thousands of customers are all suddenly offline. So forgive the data center provider, but you probably aren't going to be their highest priority right at the moment. They are focused on the physical safety of their on-site staff, working with emergency services. They're talking with the power company and thinking about proactively powering down their other buildings to prevent an even greater catastrophe. In this kind of real-time, real-world situation, there's no chance to retroactively apply high availability and resilience. Either you did your job long ago and your architecture is still holding up and your playbook is aiding your staff to methodically go through the in-the-moment issues, or your lack of planning and failure to anticipate such disasters being painfully laid to bear to all the world and to your boss's boss. In the latter case, start typing up a new resume. To make this scale of disaster comprehensible, as well as to show you that if you plan well, you never have to write that new resume, let's narrow down to one particular impacted organization. Kiwi.com, the virtual global supercarrier, can help you book a flight, a train, or a bus, or a trip interconnected across different modes of transport. They call it virtual interlining, where the technology behind the scenes organizes the means for passengers to travel on multiple carriers on a single itinerary. Pretty neat, right? So imagine you're a customer who's booked a train to take an early morning flight leaving Frankfurt through Kiwi.com. Are you going to be able to check your reservations? That morning inside Kiwi.com, their observability platform suddenly detected latencies shooting through the roof on some nodes. Then, one by one, those same nodes went dark. Each one is like taking a torpedo beneath the waterline. Each loss preventing you from operating at peak efficiency. But it wasn't just one node, or two, or three. Within minutes, as you can see from that big red number, Kiwi.com had lost 10 nodes out of a total of 30 in their distributed cluster. A full third of their capacity was not just offline. They were now smelted into a slag heap of ash and metal in Strasbourg. Yet, even as Kiwi.com lost a third of their cluster, and as their data center peers were being taken offline entirely, the rest of Kiwi.com's other 20 nodes kept running uninterrupted without loss of any data, without any performance going nonlinear. Timed out requests were simply retried and rerouted to the other nodes that were still up. Moreover, Kiwi.com maintained their SLAs for consistent throughput and low latencies. So that Kiwi.com customer checking their early morning flight, or another customer hoping to book a new trip, they never knew that the data center had burned to the ground. Kiwi.com ran a nonstop organization. This is a great high availability success story. But to tell their story in full, we're going to have to go back in time to see how Kiwi.com had planned, architected, and built their systems for just this sort of contingency. In their design phase, Kiwi.com planned to host their database on OVH Cloud, with some services placed out on Google Cloud. For their main database, they chose to use Scylla, a leaderless, peer-to-peer NoSQL system that allowed for seamlessly spanning clusters across data centers. Losing any one node didn't matter. Data was always replicated across 3 different nodes, and by the data center-aware scheme Kiwi.com chose, each replica was separately stored in a completely different data center. With 10 nodes in each of 3 different data centers, 30 nodes in all, their cluster was scalable to handle peak intraday bursts of traffic, plus it can grow with their business, plus remain fully balanced and distributed so as to be disaster-proof. And this is how it looks on the map. Each of Kiwi.com's 3 data centers had to be at least 100 kilometers away from each other to avoid any sort of regional disaster affecting 2 or all 3 of their data centers. Note the Lille data center is on the Canal de la Doule, whereas Strasbourg and Limburg lay on the Rhine River basin. Something many people didn't even think about until they saw pictures of catastrophic flooding and heard about the billions of euros lost across Western Europe this past year. So if you haven't already, you might want to ask your data center provider what their 1,000-year flood maps look like. For the record, the city of Strasbourg relies on the Erstein polder, a low-lying area that can soak up a huge amount of floodwater, about 7.8 million cubic meters. Thus, it dodged a second potential disaster this year. But let's return to March 10th and look at how things stood by the dawn of that morning. Your team has been up all night now. The span and scope of damage was readily apparent. 3.6 million websites across 464,000 domains were off the net. This included international governments and governmental agencies, businesses, NGOs. Many of those offline sites could be restored in the near term as 2 buildings, SPG3 and SPG4, had simply been powered down and could be powered back up in the coming days. Yet SPG2 was totally engulfed and SPG1 was partially destroyed and smoke damaged. Do you have any cold standby gear in other data centers? Do you keep offsite backups to get your data restored to a different cluster elsewhere? Speaking about backups, in every disaster, you have those who felt the worst brunt of all, those customers who had never done any adequate high availability or contingency planning. For a tragic number, many only that morning started checking to see if their backups were being done at the same data center or offsite, or if backups were even being done at all. For them, the loss was total and catastrophic. And while OVH Cloud has done its best to get customer services restored since, and it has even promised free backups for customers in the future, for many, the data lost that night will never be recoverable. So you would also have to have a good number of people that were surprised because they thought they had a high availability architecture, only they considered high availability as an implementation detail within the same data center, such as having a primary and replica cluster, or at best maybe rack awareness. But that's not the same as a fully distributed, peer-to-peer, leaderless, multi-data center, triple replicated system. So when your architect says that he has designed a highly available system, ask to double click on that block diagram to get to know each component in the picture. Kiwi.com's own timeline shows that there were some hiccups because while Scylla, their primary database, was resilient, some ancillary services that fed into it had some gaps. So there's some quick tweaks that they needed to make sure that they got in place by mid-morning. But for the most part, aside from their internal team sweating these details, no one was the wiser. And when we held a webinar with Kiwi.com, this is literally how they depicted their experience. With that, I hope I piqued your interest in ScyllaDB. If you haven't heard of us before, Scylla is the database of choice for high performance, low latency distributed systems. Scylla is compatible with Apache Cassandra CQL as well as Amazon DynamoDB, its API, but Scylla offers superior performance and better utility of your underlying infrastructure. We've done that by coming up with an innovative close to the hardware design written from scratch with C++. It allows for linear scaling. Our product is open source first, but we also offer an enterprise product as well as Scylla Cloud, which is a fully managed database as a service option. And by the way, if you have experience with Linux and virtualization technologies, you're probably familiar with the KVM hypervisor. It's a default hypervisor in the industry used by a lot of companies, public cloud providers. Our founders invented it. So we bring that low-level understanding of Linux design into everything we do. So who else uses Scylla? Quite possibly some of the brands you use on a daily basis, whether catching up in your latest shows, ordering your favorite cup of joe, or hanging out with your gamer buddies online. In fact, once you have a big, fast database capable of scaling to terabyte plus workloads while keeping latencies low and predictable, there are any number of industries that operate at that scale. Placing a lunch order for millions, sure. Managing time series streams from IoT devices in factory floors or vehicle fleets, you got it. Serving up content in less than the blink of an eye. Yep. Shutting down cybersecurity threats before they impact your organization, boom, done. I don't even have the time to get into all of Scylla's scalability and reliability attributes. But I invite you to check out ScyllaDB.com. You can look at our architecture, read our use cases. There's plenty to learn about how Scylla can fit into your growing data architecture, as well as your high availability and resiliency planning. But just suffice it to say that there are few, if any, hard limits. You can scale horizontally to any number of nodes, or vertically with any number of CPUs, and any amount of data per node across any number of data centers with any replication factor you feel necessary. Although we generally believe that a replication factor of 3 is fine for most use cases. So let's recap some of the lessons learned here. First, architect for disaster from the start. You cannot bolt on resiliency in the middle of a disaster, and you can't pay your way out of a complete loss of data. Second, eliminate as many single points of failure as you can. If you have, say, a database with a primary replica design, understand that you are potentially building a house of cards. Look for a peer-to-peer leaderless architecture. Third, when you say high availability, make sure it's not limited to a single data center, because that's not actually high availability. Look for topology awareness, look for multi-data center replication, and multiple customizable replication factors at that. When you're speccing out your cluster, have you considered ensuring that you can support your workload and maintain your SLAs even if you lost an entire data center? Okay, let's go further. Let's say worst comes to worst and you lose 2 or all 3 data centers in a well-designed, highly available cloud deployment. What happens then? Do you have hot or warm standby ready on another cloud? Do you have sufficient cold standby hardware and a disaster recovery plan to bring up a new cluster elsewhere if you need? Because I don't know if you've looked at global supply chains recently, but don't expect new server shipments to arrive on time these days. Also, and I cannot stress this enough, but just as you conduct pen testing for cybersecurity, you should be doing regular day in, day out chaos monkeying. Flip some switches, pull some levers, see how easy or how hard it is to break your stuff during normal business hours. In game design, they call this play testing to see if the rules break when you hand it over to the players. This is your chance to design a scenario and see what happens. Speaking of which, I want you to consider this game I've invented. It's called the Torpedo test. While we all do regular testing on throughput and latencies during POCs, do we also do failure and disaster analysis up front? Just like a submarine fires a torpedo and hits a target under the waterline, take down a node and see if your cluster keeps humming along. It does? Great. You have basic resilience. What happens if you fire away with Torpedo 2 and a second node goes offline, then a third? How many torpedoes does it take to take down your cluster? Even suffering a single torpedo, a single loss of a node, what does that do to overall performance in terms of your throughput, your latencies? What happens to the remaining system under load? Then once you've figured out the worst damage you can inflict before a cluster sinks, do the reverse. How does the system perform as you try to restore a single down node? How does it behave when you have multiple nodes to restore? How long does a full restoration take? In this brief session, it's impossible to cover every use case, every system, and every imaginable disaster scenario. But as DevOps professionals and SREs, I hope I've given you some ideas to take back to your organization and to take with you wherever in the galaxy your career leads you. I especially want to leave you with hope that even if the world is experiencing a major disaster or multiple simultaneous disasters, if you've done your homework, if you've chosen the right tech for the job, if you have your playbooks and have done your drills and you trust your team, your organization can ameliorate or even at times totally obviate the disaster's effects on your users and customers. With that, thank you. You can always follow with me at Peter Corless on Twitter. And if you want to learn more about highly available databases like Scylla, check out the free online courses at universityscylladb.com. Have yourself a great day, and as ever, onwards to adventure.